This is Gianna. Gianna is currently drinking a bottle of water that sat in the sun for hours. And right now, she's ingesting over 2,000 pieces of microplastics.
In response to the microplastic problem, we at Majipure are developing a nanocellulose-based hydrogel and immobilized enzymes which will work together to entrap and break down the microplastic particles. The cellulose is being extracted from wasted parts of food, such as pineapple rinds or even sugarcane stalk. And our system will use two different hydrogels in pairs. One which will have a more sturdy structure that will allow water at high pressures to pass through, and another one with a slightly weaker structure that will be more efficient in entrapping microplastics. For enzymes, we're taking a modified version of PTase, and this will break down PET to its monomers. The final product will consist of hydrogel beads with the enzymes attached. Water will flow through a system containing our beads, allowing microplastics to get trapped on the cellulose, thus allowing water with a significantly decreased amount of microplastics to pass through the other side of the system.
The first step in the process is to extract nanocellulose, and to do so, we begin with fresh pineapple leaves. Those leaves are cut into smaller pieces to increase the surface area, and then we start with an alkaline treatment. Basically, a sodium hydroxide solution with a concentration between 1 and 5% is prepared. The leaves are then fully immersed in the solution and heated for several hours. After this, the leaves are washed with clean water to remove any impurities, and next comes the bleaching stage. Here, basically sodium chloride is used, and also a acetate buffer is added to the solution to maintain chemical stability. This basically ensures that the fibers are further purified. The final step is acid hydrolysis, where a sulfuric acid solution with a concentration between 40 to 65% is used, and during this, the temperature is maintained between 45 and 70 degrees Celsius. At the end, nanocellulose is eventually obtained, ready for further applications.
Our extracted cellulose during its conversion to cellulose nanofibers for a hydrogel is put through a tempo oxidation process. This is important because it ensures that the hydrogel maintains its efficiency through repeated cycles of drying and rehydration. Also, we're going to implement anti-fouling measures in order to prevent the buildup of biological materials on the surface of the hydrogel, which will reduce its performance. And finally, we're going to modify the groups on the surface of the hydrogel, for example, hydroxyl groups, in order to maintain a balance between microplastics capture and enzyme
We are making use of a modified version of the pitches enzyme from Ideonella sarchensis known as fast pitches, which will break the microplastic down to its monomers of ethylene glycol and terephthalic acid, which can then be sold on to be used in other processes such as the making of antifreeze. The fast pitches enzyme already works much faster than the pitches enzyme at milder temperatures, allowing us to carry the reaction at a lower cost while still breaking down more microplastics. On top of this, we're already making further modifications to the enzyme to allow it to be able to bind to the cellulose through a carbohydrate binding module.
So, how do we actually ensure that the enzyme does its job well? As mentioned before, it does take a very new and niche role in this fight against the microplastics. So naturally, it should be taking a rather new and niche form, right? And that's where we at the Enzyme Design Lab actually come in. We choose to design this in two new ways. Firstly, we improve its structure to allow for the binding of the enzyme to the cellulose structure. Secondly, we also design it to improve its activity as well as its thermostability. Getting onto the first one, by modifying its structure to include a structure called a carbohydrate binding module, we allow it to bind to the cellulose structure. And this allows for more active degradation of the microplastics as we're collecting them. And this allows for a quicker degradation process and faster results. Secondly, we seek to improve its activity as well as its thermostability. So this means that we're trying to increase the rate at which it's capable of degrading the plastics. And this allows for a quicker process and faster results. And by improving its thermostability, we seek to increase the range in which it's able to work. And this means that it can work in more different temperatures than it was previously capable of. So we could have degradation of plastics in areas that are temperate, tropical, and potentially Arctic.